My name's Eric. I'm with the AWS security team. I've been with Amazon for about 12 years, and for the past couple of years, the security industry as a whole has had a very interesting time of it. We're at the beginning of what I think is a new era in computing. Over the past couple of years, we've been introduced to a new class of practical attacks that have serious implications for how we build software and hardware. The end of 2017 and the beginning of 2018 saw the first wave of these new issues, but 2 years later, we're still seeing new papers with research in this area, and it's going to continue. So let's look inside a computer. We've got CPU, and we've got memory. RAM is fast, right? But CPUs are faster. There are processors out now that are 5 gigahertz all cores, and a good rule of thumb is that the speed of light in copper is about a nanosecond a foot. And that means that a clock cycle now is physically shorter than a memory module. From the perspective of the CPU core, RAM is almost glacially slow. Accessing memory can take hundreds of clock cycles. So just like the drawings of the solar system, when you draw this to scale, it looks a lot different. The whole job of the entire computer is to keep the CPU saturated with instructions. That's what we're trying to accomplish. And so a block diagram of a CPU, you're going to have something that looks a little bit more complicated than this. Instructions need to be fetched from main memory. They need to be decoded. The processor needs to figure out what it's doing. Then there are the functional units that do whatever it is that the processor does, adds, loads, multiplies, cryptographic operations, whatever functionality the CPU supports. And then there's the register file, which is a small amount of memory that runs at core speed. Most instructions operate directly on registers. And so we want to keep this saturated with instructions and with their operands. So here's a little snippet of assembly. What we're going to do is we're going to add two 64-bit values that are stored in consecutive locations in memory. So this move instruction requires two memory accesses, one to fetch and decode the move, and the second to actually perform the move from memory into a register. The add only requires one memory access. Second move is another two memory accesses, and finally we can perform an add. So we've performed 4 instructions, one add, and if memory accesses take, say, 200 clock cycles, it's taken us 1,200 clock cycles to execute these 4 instructions. CPU utilization is less than 1%, which is terrible. At this point, clock speed basically doesn't matter. The bottleneck is not instruction speed, it's fetching data from main memory. And there are 2 techniques that we're going to talk about today that are used to improve the utilization and to drive up CPU saturation. The first technique is caching. The key realization is that most code observes locality of reference, both in time, data that's referenced is likely to be referenced again, and in space. Data that's accessed is more likely to be close to data that's already been accessed. By having a relatively small cache, on the order of megabytes to tens of megabytes, that's physically close, literally on the die, and pretty fast, you can get a cache hit rate that's in the high 90%. And this diagram is not out of scale. Here's a vintage 2014 desktop CPU. It's got 18 cores, 16 hardware threads. Not marked on this diagram, inside each of the cores, there's a first cache, an L1 or level 1 cache that runs very close to core speed, a larger but slower L2 cache, and then this big block in the middle that's labeled shared L3 cache. It's the level 3. It's also called the LLC or last level cache. Die area is the main constraint in building a processor. More area means more power, lower yield during manufacturing, fewer chips per wafer, which drives up cost. The main memory latency problem is so central to chip design that a large chunk of the die is dedicated to hiding latency to main memory. The other technique to hide main memory latency and other latencies is out of order and speculative execution. So if we look at a couple of instructions here, let's say that Y is a slow load. It's not in cache. Well, X is present in both of these instructions. We can't start calculating Z until we know the value of X. This is known as a data dependency. So the processor is constantly scanning the instruction stream, looking for instructions that can be reordered. These instructions cannot. However, if we look at another example, Y is once again a slow load, the processor can and will reverse these 2 instructions. This is out of order execution. This is not an unusual thing. The processor is constantly reordering instructions, executing everything that it can as early as it can so that it can have as much time as possible to allow the slow loads to happen. And so this is the normal state of execution of the processor. Now, it's important to know that the processor doesn't execute C code or any other higher level language. It executes assembly language, it executes machine instructions. And so here we've got the same data dependency, but Y and Q are both slow loads. In this case, the processor is going to issue the load for Q well before the value for X is resolved. And so we are reordering things within the level of statements in any high-level language, but also modern Intel processors on the fly decompose instructions, x86 instructions, into what are called mu-ops or micro-ops, and it reorders those. And so again, we're going to get out-of-order execution here, even though we still have the data dependency. In a special case of out-of-order execution, again, Y is a slow load here, but we can calculate Z. We may or may not need to calculate Z, but we can calculate Z. This is speculative execution. The processor doesn't want to stall. There's an instruction that it can calculate. It is going to speculatively execute that instruction. And again, this is common. This is how your processor is running all day, every day, whenever it's running code. If we guess correctly, if it turns out that that loop guard is true and the body should have executed, then we retire those instructions. They are committed to the architectural state of the processor. If we guess wrong, then all of the architecturally significant side effects of the instruction are rolled back. Architecturally significant here is the documented interface to the processor, the ABI, the set of instructions, the things that are documented for interacting with the CPU. But the cache contents are not architecturally significant. Any changes to the cache as the result of speculative execution are not rolled back. Now, that seems fine, right? I mean, the cache is defined in the microarchitectural state, but not in the architectural state. There's no instruction to say, is this data in cache or not? So we should be okay here. But remember, main memory is glacially slow. We may not be able to explicitly ask, is this data in cache? But the response time between a cache hit and a cache miss is significant. Using timing, we can make microarchitectural state visible architecturally. So we've got a chunk of code here. What we're going to do is we're going to allocate an array. And I couldn't draw 256 boxes. PowerPoint got mad at me, but pretend there are 256 of them. And then we're going to walk across them and we're going to flush them from cache. So they're present in main memory, they're not present on the processor die. Then we're going to tell the processor to go do something expensive, but that we know is going to evaluate to false. This is going to kick the processor into speculation. And then this line here, it's red because it's not actually executing, it's executing speculatively. And this is the whole catch. This is the crux of this concept. So pointer could be any value, any pointer to anywhere in my address space. We're going to dereference the pointer. We're going to get the value stored at that pointer. We're going to multiply it by page size, just so the processor doesn't optimize out anything. And then we're going to fetch the probe array entry at that offset. And I assign it to garbage. I don't actually care what it is, because expensive but false evaluates to false. This line is never going to execute architecturally. But because we accessed an element of the probe array, it's been pulled into cache. And so then I can walk along my probe array saying, how long does it take to access every entry? And you get a graph that looks like this. And so based on this graph, it is clear that the value behind the pointer was about 82. It's a very clear signal about the microarchitectural state that's architecturally visible. So let's talk about why this is a big deal. 2 to the 36 is 64 gigabytes. This is physical memory on a server. And when the machine boots, the operating system, the kernel, is going to load itself into memory at some set of addresses. And it's going to go multi-user, and it's going to start offering services. And then I run a process. My process gets its own 64-bit virtual address space. I get my own 2 to the 64, and 2 to the 64 is massive. If I allocate memory in my process, that's going to be allocated in my virtual address space, and there's going to be a mapping to a bunch of physical pages. Likewise, if you launch a process, you allocate memory, there's a mapping from your virtual address space to a set of physical pages. In order to make it easy for the OS, for the processes running on the operating system to request services of the kernel, and it simplifies a bunch of other memory mapping tasks, operating systems have traditionally mapped the entire physical address space into every process. And so my yellow memory is there explicitly in my virtual address space, but there's also a copy of it and every other piece of physical memory in the mapping of the entire physical memory into my address space. Now, this is safe because the virtual memory system has permissions bits on it. If my unprivileged code executing in my process attempts to access the physical memory mappings, I get a segmentation violation. If I don't catch it, my process crashes and I don't get to access kernel memory. So let's put these two together. Once again, we've got our probe array. We're going to flush it from cache. And then I call begin transaction. This is the transactional synchronization extensions from Intel. Just like a database transaction, TSX guarantees that all of the instructions in the transaction either execute or do not execute atomically. And so I enter my transaction, and then I execute the same thing. I dereference a pointer, this time into kernel space, and that's going to throw an exception. It's a segmentation violation. But these instructions are already in flight, and the transaction is going to get rolled back. There's already logic on the processor that's going to prevent me from accessing kernel memory, and it would take more transistors and more complexity in the processor to halt these in-flight instructions. So the speculation continues, and I access the value behind the pointer. I use that to index into my probe array. I pull an element of the probe array into memory. Now eventually, the processor figures out that there's a segmentation violation. My transaction gets aborted, everything gets rolled back. There's no architectural state change to the processor, but the cache state has still been perturbed. And so now, when I check cache timing, again, I can tell what the value behind that pointer was. Now, this is the fancy version using TSX. The simple version, rather than just probing inside of a transaction, I can have a process that does the cache flush and then does the probe and crashes. It accepts the seg fault, killed by a signal. The cache state has still been perturbed. And so I can probe and crash. It's more expensive. I have to launch a whole bunch of processes, but you don't strictly need TSX to do this. This is Meltdown. We accessed speculatively restricted memory before the permissions are checked. They were eventually enforced. I didn't actually get kernel memory in the architectural state. I only did it while I was speculating. But I used that as the index into an array that was not present in cache, pulled one of the entries into cache, and then I could tell the value of the restricted memory location. Fundamentally, this is a creative act. This is a set of researchers that put together the building blocks that we've all had access to for years in new and exciting ways. And so I didn't actually access any kernel memory. Everything was rolled back and aborted with an exception. The architectural state remained intact. I didn't use any other CVEs, any other vulnerabilities with this. It's just a bunch of if statements. There's no special requirements here. I just executed code. And there's not going to be any logs as a result of this. I mean, maybe there are logs if you're launching a billion processes because you're doing probe and crash, but the version with the transaction, and there are other versions that don't require you to crash, it's just processing. It's just looping across memory locations. The thing that I love the most about these attacks is that the real world has finally caught up with Hollywood. These attacks are slow. And so all of those terrible movies where the music is getting tense and the little thermometer is crawling across the screen and everyone's screaming, let's go, hurry up, that's how these attacks work. I don't think they have theme music. But the leakage rate of these attacks is in the order of kilobytes to tens of kilobytes. And so walking across a large memory space can take a long time. The other thing is that these are probabilistic. So the modern systems are large, they're noisy, there's a lot going on. And so you're not guaranteed that your perturbation of cache state is going to be the only perturbation of cache state. And so they aren't perfect. Sometimes there are mistakes in what you measure. One major CPU manufacturer's processors were affected by this. The other major CPU manufacturer's processors were not. Why? We don't know. I mean, someone somewhere knows. Someone deep in the bowels of these processor manufacturers knows, but this microarchitectural detail is considered proprietary by the processor vendors. And so were they trying to check permissions early because they were worried about this kind of attack? Are there fundamental differences in their microarchitecture that just made it not apply? The public does not know. So this is a processor bug. It's beneath the operating system. Linux was affected exactly as I described. Windows doesn't have exactly the same memory layout. There's not a single contiguous block of physical memory mapped, but for all intents and purposes, it's the same. There are multiple mappings that contains most of physical memory. Mac OS was affected exactly as described, as was Android as a Linux derivative. In addition, none of the privilege constraints, the privilege management capabilities, et cetera, of Docker did anything to stop this, because we're not making any requests of the operating system. We're not making any system calls. We're not doing any I/O. It's just processing. The fix for all of these was to remove unneeded memory from the memory map. And so there's still a set of addresses that need to be present in order to make system calls and things like that, but those and only those addresses are present. Reading out the address space via speculation is still possible. There just isn't anything there for you to find that you shouldn't be able to read. In Linux, this is called KPTI, kernel page table isolation. So let's speculate a bit more. Nice little block of C code here. This is not what the processor executes. There's no if statement in assembly. And so this is one possible set of assembly that a compiler could issue for this set of C. So we're going to compare a register against 0. If the two are equal, we jump to loop false, etc. This is an unconditional branch. You always jump to the label. And so it's easy to speculate past this. We know the next instruction to be executed. It's not the next instruction sequentially. You just go to the label. And so speculating past this branch is easy. This one, though, is called a conditional branch. Branch if equal, jump if equal. And so we may execute the add. We may execute the subtract. We don't know. But we want to execute something. We don't want to stall the pipeline and wait for this comparison to finish. You know, what if X is a slow load? We may be hundreds of cycles before we can continue executing. And so we're going to go down one of these two paths. And we can guess, but this is where branch prediction comes in. And again, branch predictors are proprietary internals of CPU microarchitectures. They are not disclosed. There's active research in reverse engineering them. But there's some very basic realizations. So most if statements are error conditions. They never happen. And if they do happen, it's an unhappy case and you don't care if it's slow. For loops and while loops go through the bodies multiple times typically. And so the simplest branch predictor is just go the same way you went last time, and that's usually right. Branch predictors get more complex, but for all of them, basically, if the branch goes the same way many, many times in a row, the predictor will be trained that the branch is going to go the same direction next time. This is Sally. She was a good girl. She's been gone for a few years now. But in her prime, she played a mean game of fetch. And I'm a terrible person. And so when you're playing fetch with a dog, you throw the ball and the dog runs. And you throw the ball and the dog runs. And you throw the ball and the dog runs. And then you swing your arm, but you don't let go of the ball, and the dog still runs. This is exactly what we're going to do to the CPU's branch predictor. So here's another chunk of code. Again, we allocate a probe array. We allocate another array this time. It doesn't really matter what it is or how large it is. There's just some memory structure that we own. And that memory structure has a size. And we've got this fetch function here that dereferences our array and returns with our meltdown style array dereference. And so we're going to call fetch 3. Well, X is less than buffer size. And fetch 7, X is less than buffer size. And we do this many times, however many times, and we can empirically experiment here and determine how many times our branch predictor needs in order to be trained here. Then we flush the probe array from memory, and we call fetch on some arbitrary location. It can be before my array, it can be after my array. In this case, it's well off the end of the array. And so we call into fetch. We're waiting to determine if X is less than buffer size. We're going to speculatively execute this line. So we pull buffer of X, which in this case is an arbitrary memory location, multiplied by page size again to prevent the processor from optimizing certain things. And that's going to result in pulling one of these cache lines into one of these probe array entries into cache. Now, as written, this is a useless attack. It's widely applicable. All I've used is branch prediction and speculative execution. Pretty much every modern processor is affected by this. But it's a useless attack. I have, via a very convoluted path involving speculative execution and timing, given myself the privilege to access all of the memory in my process. But that's where I started. I mean, that's the definition of my process. So why does this matter? There are places where you can execute code, but you don't have access to the full memory of the process. And the most common case here is browsers, the JavaScript sandbox in a browser. Traditional browsers ran one process for the entire browser. All of your tabs, all of the functionality that's supported in that browser is running in a single process. Take the code that I had in the last slide in C, port it to JavaScript, hack on it a little bit so the JavaScript compiler doesn't optimize out things and actually does what you want it to do, and it's off to the races, literally. If I can get my JavaScript executed in your browser, I can walk the entire address space of that browser process beyond the JavaScript sandbox and extract everything in there, including history, cookies, autofill information, etc. Now, again, these researchers are clever. They're intelligent people that are doing creative things. There's no cache flush instruction available from JavaScript. And so what we've been talking about is flush and reload. We flush the probe array from memory, and then we cause one of them to be reloaded into cache. Well, caches in modern processors tend to be set associative. There's a limited number of cache lines that a given memory location can be loaded into, and it is possible empirically to determine what the mapping function is. And so you can just access enough memory such that you are guaranteed that the probe array has to be evicted from memory, and then you can do the reload operation. The other thing is that there were no high-resolution timers in JavaScript, and you need time in order to determine if the access of the probe array entry was fast or slow. Well, they just created a new web worker thread with a countdown timer, and the delta between a fast access and a slow access was large enough that there was enough signal there. And it's important to know that adding noise to a channel doesn't destroy the channel. It just lowers the bandwidth of the channel. Sometimes that's a sufficient mitigation if you can bound the execution time, but sometimes it isn't. And again, this is a fundamentally creative act. So we've got this picture here of JavaScript running in the browser. Well, there's an identical picture with identical consequences. BPF is the Berkeley packet filter. It was originally designed so you could load packet filtering code dynamically into the kernel. eBPF is enhanced BPF. It's much more functional. And again, you can dynamically load code into the kernel, and it's supposed to be safe. eBPF won't load code that it can't prove terminates. The general halting problem is impossible, but you can prove that some programs terminate. eBPF will not load a program that it can't prove terminates. And it won't load any code that has instructions that are unreachable. And so it's safe. But this picture looks just like the JavaScript sandbox with exactly the same effects. And there's another clever tidbit I'd like to highlight here. So we've got our buffer size. We're going to check if x is less than buffer size, and we want to win the race. We want the processor to be off speculating for a while. Well, eBPF is reference counted. Data structures in eBPF have a reference count associated with them, and those data structures can't be reclaimed until the ref count goes to 0. And so this is hosted on some core in our processor, and we've got our x is less than buffer size check. Well, Intel cache lines are 64 bytes long, and it turns out that when the compiler laid this out, the reference count and the buffer size are in the same cache line. This is called false sharing. So what they did is on another core, they loaded an eBPF program that just referenced this array and then unloaded itself. And so in order to do that, they had to negotiate the transfer of that cache line over to the other core so they could increment and then immediately decrement the reference count. Well, now the cache line is over on the other processor, so when we execute our check against the buffer size, you can see the buffer size is cached on the other processor. And so now we have to use the inter-process cache negotiation protocol to get that cache line back, and it increases the odds that we win the race. Again, this is fundamentally a creative act. This is Specter Variant 1, and I love the fact that the ghost is holding a branch. We didn't actually access any out-of-bounds memory architecturally. It all happened during speculation. Again, no other vulnerabilities were used. It was all executing in the context of my process with no privilege escalation. And all I needed to do this was a processor that speculates, if statements, looping, and some notion of time. These are really low requirements. And so we're not relying on implementation choices deep within the processor to allow us to peek at restricted memory while speculating. We're just poking around in our own process's address space, but that allows us to bypass intra-process memory restrictions like sandboxes. pretty much anyone that builds a CPU that does speculation, and this is pretty much everything other than some small embedded chips. The glory of these attacks is that my 486 is completely immune to all of them. And which has non-architectural state that can be measured, is going to have Spectre-style issues. So let's hit one more. This is an indirect branch. And if you unpack this, this means take the value in the array, use that as a pointer to memory, fetch the value in that memory location, and jump to it. So it's not jump to the contents of the register, it's jump to the contents of the memory pointed to by the register. These are not uncommon. They're issued by the compiler for things like polymorphic code or switch statements. With the information we have here, this is impossible to predict. Literally anything can be in this register, and literally anything can be in that memory location. And so we don't want to stall, but we have no idea where this is going to go. And so the processor has another functional block here, a branch target buffer. And again, just like the branch predictor, the branch predictor that we were playing fetch with earlier, the implementation details are complex, and people are actively reverse engineering the branch target buffers in various processors. But just as we did with the regular branch predictor, if you take the same path enough times, if you play fetch long enough, you can train the branch target buffer to go where you want it to go. And so let's hit one more attack. And this one is a little bit involved and I think a lot more clever. And so we need a target. We need something with access to interesting data. This can be a kernel, this can be a hypervisor, this can be another process that we can make calls into but we don't have access to. Then in that target, we need to find an indirect branch. That branch has to be invocable. And what that means is we have to be able to steer execution to that branch. We have to be able to cause the processor to reach that. The program counter has to point at that branch. And we have to have control over some processor state when we reach there. And the simplest, easiest assumption is that we have control over 2 registers. That assumption is sufficient. It's not necessary. There are other assumptions that result in similar outcomes. And then finally, we have to find a gadget. And this gadget doesn't have to be in our call path. It just has to be in the same address space as the indirect branch in our target, and the page it's in has to be marked as executable. It doesn't matter if this gadget gets called in the normal course of execution or not. It just has to be something that we can cause the branch to vector to. If you've heard of return-oriented programming, ROP, this is somewhat similar in that we're borrowing instructions for purposes for which they weren't intended. But because our gadget only ever executes speculatively, we don't care what comes after the gadget. It does not have to be followed with a return instruction. It just needs to do the things we want, and it can be as short as 2 instructions. Basically just setting up the initial array access to access off of some pointer so that we can access some memory location, and then accessing an array based off of that value. And this is a fairly common sequence of code to be issued by compilers. And so this looks like a niche attack. This looks complex, but it's not. One of the key realizations here is that pretty much all code is linked against tens of megabytes of shared libraries. And so if, for example, you found a common call in libc that had an indirect branch in it, and then anywhere else in libc you found a gadget, then any process that's linked against that version of libc can be exposed to this. Again, you have to find a branch that you can cause the processor to eventually execute. But given the wealth of shared code in most processes, this is actually a surprisingly applicable attack. And so here we've got something. We'll call it a kernel. And so there's an indirect branch there at 3FC2. And so that's our indirect branch. It's in a function called do.io. That may be in the process of handling a system call for writing to disk or the network or something like that. But it's something that we can call into. And by tracing execution, we know that ECX and EDX are unchanged from what they were set to when we initially made the system call. And this isn't unusual because registers are saved and restored on function entry and exit. And so this is not an unusual precondition. This branch is invocable. We can cause the processor to execute it. Then we find a gadget. This has to be reachable. It has to be in the same address space, but you can see it occurs before do.io. It may be that this is actually dead code that's sitting there in the binary and never actually gets executed, but it's there. It is in a page that's marked executable, and it does what we want it to do. So now that we have a target branch and a gadget, we set up our own process. So we're going to load the address of our gadget into the memory location pointed to by a register, and then we're going to jump to our indirect branch. And our indirect branch is going to dereference the memory at that register, and it's going to jump to the address of our gadget. Now, a real implementation would be more complex, and it would be harder to fit on a slide, and it would have a loop where you only did this a certain number of times. But you can actually do it this way. You can just have the infinite loop training the branch target buffer running in the background. And so if we do this enough times, we're going to train the branch target buffer that the indirect branch at 3FC2 goes to 2C30. And the number of times is in the tens, typically. And so now we've got our trainer running. We've got the branch target buffer trained. It's time to do it. So we set up our probe array, make sure that it's not cached. We covered how to do that. Then we set up our call into the target. So target offset is the memory location that I want to access. And we're probably going to have to add or subtract an offset from it. In this case, if you look at 2C30, there's an array there. This is some data structure in the kernel. And so I'm going to have to subtract the value of the base location of that data structure from my target offset. But that's easy enough to do. So I load the target offset, and I load the probe array into registers, and then I call into my target entry point. I make my system call or whatever it is that I'm going to do. And so now, eventually, the program counter reaches do IO, it's doing stuff, and it's going to get to this indirect branch. Well, we don't want to stall. We're going to consult the branch target buffer. Well, the branch target buffer tells us to go to 2C30. And so while the processor is busy figuring out what's actually stored in the memory location in register A, it's going to speculate into our gadget. And again, this is speculative execution. This is not happening architecturally. It's just in case the branch happens to go the same direction. And so we're going to access some offset off of some kernel data structure, and we control that offset. Then based on that offset, we're going to access an element in our probe array that's going to pull one of the entries in the probe array into memory. And so this is a little bit more complicated. We've introduced the branch target buffer, we've introduced the indirect branch, and we've introduced the gadget. We have to find code that performs part of our attack that already exists inside of the target. But because all of these accesses are occurring in the kernel, they have access to memory to which my unprivileged process doesn't have access. And so we don't care what happens after this. I don't care what the next instruction is after 2C32. It doesn't matter. The processor can continue to speculate on as long as it doesn't pollute the cache, as long as it doesn't pull another element of probe array or push this element of probe array out. The processor is going to do a bunch of work speculatively. Eventually, it's going to resolve what's in register A and what's in the memory pointed to by register A. And then it's going to jump there, and it's going to discard all of these instructions as if they never happened. But the perturbed cache state is going to persist. That's not going to get architecturally rolled back. This is Specter Variant 2. Once again, there are no logs here. There's nothing to look for. We mistrained an indirect branch in one context and then use that indirect branch in another context. Now, the branch target buffer is a per core block. And so if I train the branch target buffer on one core, and then in another core someone jumps into the kernel or the hypervisor, their branch target buffer won't be mistrained. It has to be done on the same core. Then we used instructions that already existed inside of our target as a gadget to perform functionality that we needed. And finally, again, the memory was only ever accessed speculatively. It was never accessed architecturally, but it was done in another context. It was done in another privilege level. This is pretty straightforward in most all modern processors. Certainly anything in a laptop, desktop, server, or phone. And so impact across the industry here was broad. Now, I've focused on cache timing as the side channel, but pretty much anything that can be measured can have a side channel associated with it. And so there are ways you can set up this attack such that if an instruction executes quickly or if it executes slowly, you can tell whether or not the processor state was here or there. There are a number of execution units in the processor. You can go read the data sheets on the latest processors from every vendor, and they'll say, oh, well, they've got 3 loads and 4 store units and 2 adders. And you can constrain, by cleverly scheduling instructions based on the contents of memory, you can occupy or not occupy the ports on those execution units and have timing differences. Sometimes blocks on the processor get powered down. It was one of the new Core i7 processors. The power management unit on that processor had more transistors than a Pentium in it. And so as the processor is dynamically powering up and down blocks, you can tell if that block has recently been used. And if you can cause that block to be used based on the contents of memory during speculation, you can tell what that value was. Likewise, the branch target buffer isn't the only functional block on the CPU to watch. There's a line fill buffer that's responsible for filling cache lines from main memory that has timing side channels. The load ports, the page tables, Specter Variant 4, I think it was, Foreshadow, which Intel called L1 terminal fault, relied on behavior of the page tables. So, I just told you a terrible story of gloom. There are multiple flaws built deep into all the chips that we use. Surely, if it's as bad as I say, then we're all doomed, right? Well, the world learned about these issues in early 2018. We were actually working on them for a significant period of time before then. It's been almost 2 years, and we're still here, so at least we have an existence proof that if our doom is impending, it's happening slowly. A large part has been due to hard work by people across the industry, including Amazonians. And this was spectacular to watch in practice. Like, literally all of the major internet players were involved in fixing this, working together to the mutual benefit of our customers. So let's dig into the implications of what we now know. If you're going to host untrusted processes, do it in a VM. EC2 instances are hosted in VMs, but years ago, we took the decision that if we were going to host a process that we didn't control, we were going to do it in a VM. And this turned out to be a good choice. Traditional VMs live a long time. And so in EC2, if it takes your instance an extra 10 or 15 seconds to boot, it's not a huge deal. But for Lambda and Fargate, our function as a service and our container task as a service services, that extra startup time was significant. A Lambda invocation can last milliseconds. And so the impedance mismatch between EC2 instances and these short-lived tasks was significant. And there was tremendous business pressure to drive up density, drive down latency, and decrease cost. And containers or other packaging technologies were really attractive here. But we felt so strongly about this that we built our own hypervisor specifically for these ephemeral tasks. It's Firecracker. It's available on GitHub. I encourage you to check it out. It's powering Lambda and Fargate today. And so in EC2, in Lambda, and in Fargate, we never have customers sharing processes, address spaces, or virtual machines, unless you as a customer choose to do that. So again, if you're going to run an untrusted process, do it in a VM. If you're going to host code, host the code in at least a separate process, if not a VM. And this is a nuanced space. This is the lesson that we're learning with Firefox now. They're undergoing something called fusion, where they're following Chrome's lead and going to a process per site model, where they're going to split up address spaces based on the security context. But be really careful here and evaluate your choices deeply. The attacks that we talked about here are creative and subtle and leave no trace. Clever people can come up with ways to time things even in the presence of blinded or coarse timers. They can figure out how to win races by exploiting false sharing with cache lines. Even if you think the processing in question is trivial and lightweight, for example, simple personalization based on HTTP headers, there's risks to be considered. Headers contain sensitive things like cookies, and even if you aren't processing the headers in your code, if your cookie is present in the same address space as code controlled by someone else, it may be leaked. And there are a lot of places where we host code. For example, in Redis, you can have user-defined functions. Well, a user-defined function supports looping and all of the constructs necessary to pull off one of these attacks. Redis doesn't have much in the way of an intra-database process or access control model, and so it's not a huge problem. There's no notion of privilege escalation, but it's just an example of a place where code is being hosted. even serial monogamy may not be enough here. I'm never going to have two customers running in the same process at the same time, so I'm going to handle customer A, and they're going to leave, and then I'm going to handle customer B. Be really careful there, because processes weren't designed for this. You have to be absolutely certain that all of customer A's state was flushed from memory before customer B gained access to that address space. This is a really nuanced thing to deal with. One place where this comes to the fore is CDN edge processing. A CDN is a content distribution network. Content distribution networks rely on a large number of small points of presence, or POPs. These tend to be capacity constrained physically by power or floor space, and massively multi-tenant, with thousands to tens of thousands of customers operating on perhaps only tens of boxes. And so the cardinality of customers and customer functions per box is very high. And it's fast and cheap to cycle customer invocations across a set of persistent processes. But unless the computation supported by the CDN is significantly limited, and I mean significantly limited, then this can be unsafe. As we saw earlier, the preconditions for these attacks aren't complex once you have the ability to execute code in a shared address space. So this is the same block that we had earlier. And eventually, this processor is going to stall. No matter what we do to try and predict the future and to make sure that we preload everything we can. And so what the processors manufacturers do is they add another set of architectural state registers and the other state bits that are necessary. And so this processor is going to run until it stalls, and then it'll yield, and then this processor will run until it stalls. This is called SMT, symmetric multi-threading. Typically, it's 2 threads per core. Sun's Niagara went up to 4 a number of years ago. Intel calls this hyperthreads. This is about as much sharing as you can get at a hardware level. This creates the greatest possible surface area for side channels and trainable CPU internals. We have never shared the 2 threads on a core between EC2 instances. On some older instance types, we do split the threads on a core between DOM0, our control plane, and a customer instance. But in that case, we've written a co-scheduler such that our control plane and the guest never run at the same time. Basically, while the hypervisor is running, we treat the core as single-threaded. And so if you're going to host multi-tenant workloads on SMT-capable CPUs, either disable SMT or otherwise ensure, maybe via the co-scheduler that I described, that workloads from different tenants never run on the same core at the same time. None of the CPUs, the Graviton, et cetera, CPUs made by AWS have SMT, so this doesn't apply to them at all. I stole these slides from Anthony Ligori's Nitro deck from a few years ago. This is a block diagram of an EC2 physical server before we started on Nitro. And you can see there's a lot of our control plane processing happening on the x86 host. We still have full faith in the security of these hosts, but it's taken a lot of work. We've been deeply engaged with the research community, working with them to validate their findings, to completely understand the implications, and to make sure that the patches actually accomplished what they needed to accomplish. So we've developed a lot of mitigations to these issues here, many of which we've shared back to the community. But because we're sharing processors, buses, caches with guests, we have to evaluate and respond to each of these new research papers, each of these new findings. So we believe that AWS is the best place on earth to run virtualization. Not a shocker to hear that at reInvent. But wherever you choose to host your workloads, make sure that they have a team that is aggressively and continuously keeping up with new developments in this area. And make sure that you keep up with your security patches. The C5 is the first instance type that we launched that ran the full Nitro stack. All of our control plane activities have been moved off of the x86 and onto chips built by our own Annapurna labs. Our control plane is now running on physically separate hardware from the guests. The Nitro hypervisor was purpose-built for this. It has no processors or memory allocated to it statically. It executes only in response to calls from the control plane. And so this has greatly reduced the surface area between guests and our infrastructure. And the increased isolation provided by Nitro has allowed us to respond to many of these new papers with no impact. This hasn't decreased our engagement or vigilance, but we've seen significant return on investment in the improved isolation of Nitro. And for the ultimate in separation, we have our bare metal instances. Because the entire control plane, all of our code, is already running on our own chip, separate from the x86, and because we completely control the hardware and the boot process via the Nitro security chip, we can confidently and completely hand the box over to you as a customer. In this case, there's no Amazon code running on the x86. You can run your own operating system or hypervisor, including Firecracker, if you want to. For obvious reasons, we can't offer this in smaller sizes, but you get all the physical security benefits of our data centers, all of the locks and alarms and fences and guards, direct local access to our network, VPC, EBS, all of our other services, but you have complete control over the x86 host. So what did we do as a result of this? Well, first of all, this is the last nail in the coffin of paravirtualization. Paravirtualization is what put Xen on the map, and it's awesome. It's basically you alter the guest operating system so it cooperatively requests services from the hypervisor when it needs to make calls. And this worked great in the days before we had full hardware virtualization support on the processors. The problem is that much like the entire address space is mapped into every process, the memory sharing between the hypervisor and a paravirtualized guest is unsafe in the face of Meltdown. And so this meant the end of paravirtualization. Rather than terminating a bunch of customer instances and telling people to upgrade, we built a shim layer called Vixen. And so we run a hardware virtualized guest. Inside that guest, we run Vixen, which presents a paravirtualized interface to the unaltered EC2 instance. So you can continue to run paravirtualized EC2 instances. They're still out there, but you should not. All of your paravirtualized instances should be terminated, moved over to hardware virtualized. Within a paravirtualized guest, it's very hard to make any security guarantees anymore. We can make very strong statements about the security of attacks from a paravirtualized guest to other guests on the box or to the host itself, but within a paravirtualized guest, it's time to move on. We built Vixen. That's not what wound up being upstreamed. The thing that wound up being upstreamed and pulled into the mainline Linux kernel is called Comet, and there are pieces of Vixen in Comet. Indirect branches. Paul Turner at Google came up with retpoline. This is a really clever thing. I encourage you to read the Google blog post about retpoline. It's a portmanteau of return trampoline. And it's basically a clever construction that relies on the fact that the branch predictor used for predicting the target of return instructions is higher priority than the branch predictor used for predicting indirect branches. And so if you speculate into an indirect branch, it trampolines you off to a block of code that's a benign infinite loop. And speculation does nothing. But if you actually execute it, it causes you to return to where you wanted to go. It was an Amazonian, David Woodhouse, who actually implemented these changes into GCC and LLVM. And so in order to defang indirect branches, you had to get the updated compiler, and then you had to recompile things. And so we had to rebuild hypervisors, kernels, operating systems, the Amazon Linux AMI, et cetera. Again, keep up with your security patches. This is really clever. It stops speculation dead, and it has an overhead of only a few instructions. And then, as I mentioned earlier, we unmap unneeded pages in the memory map. If you don't need them in your memory map, get rid of them. And this is kernel page table isolation in Linux. Side channels have been a thing in computer science for decades. Consider a naive password checking algorithm. So you've got a password, and you've got a candidate password. Well, you check, and if the first character matches, you move on to the second, and if it doesn't, you bail out. Or if the second character matches, then you continue. If not, you bail out. Well, based on the timing there, I can tell how far you got into that password. This password checking algorithm is not constant time. It has a side channel. The execution time of the password checking algorithm depends on a secret input. And so I'm exposing something about that secret input. And if I can guess character-wise rather than having to guess the whole password, that greatly reduces the complexity. It's very easy. And so we have SideTrail. This uses an SMT solver. It's from our automated reasoning team. And it does an exhaustive symbolic search of the input space. And it understands the length of all of the execution paths. And it will either tell you this function has no side channels or no significant side channels. You can give it a threshold value. Or if there is a side channel, it'll give you a pair of inputs that have a significantly different timing. And so it's also on GitHub. There's a nice README file. If you are writing code that processes secrets, that has cryptographic algorithms in it, I suggest you check it out. This is really the bottom line for this talk. Hopefully, at this point, everyone knows that crypto is not for amateurs. I strongly encourage you to learn more about encryption. I myself am a shade tree cryptographer. I know enough to be dangerous, to understand the challenges, the clever attacks, the way that people have very cleverly found a tiny little corner that they could peel back and turn into a practical attack. And the mitigations and the decisions that have led us to the set of cryptographic primitives and protocols that we have today. However, when it comes to designing those primitives and protocols, leave it to experts. There's no room for amateurs there. I gave a talk at this about reInvent a couple of years ago. You not only need a team of experts to get you started, you need to keep them on staff so that as the world changes and as new discoveries are made, you can adapt and adjust and keep your cryptography up to date. The same thing now applies to computation. It is no longer a space for amateurs. We've always realized that compute virtualization is not obviously hard. And what I mean by that is it's obviously hard in various ways, but there have always been subtle ways to make mistakes, especially when doing it in production and at scale. With the release of these papers, we've learned that getting it right is even more challenging, and that right is a moving target. Since Spectre and Meltdown were released, there's been a constant stream of papers applying these techniques and similar techniques to other parts of the CPU and of the system. If you're going to host code, whether it's virtual machines, function invocations, JavaScript, even if it's something as simple as transforming the headers for a web request, you need a team of experts. And I mean people that didn't attend this talk because they would have found it boring. And you need to have those people around, and you need to keep them around for the foreseeable future. And you need a budget for pushing out patches, reading papers, and reproducing issues. You need to either hire these people, or you need to choose a partner and a provider that you trust and that has these people on staff. Now, you came to reInvent to learn. There's no need to stop when you go home. We have a whole bunch of training courses for you, 30+ free training courses. And so I encourage you to check out all of the learning opportunities both here at the conference and the resources we make available online. And thank you very much for joining us on this first day of reInvent.